Hi, I'm Gary, and I want to show you how I use Cloudy. Okay, let's set up a model for the M16 cloud. This is the famous the HST image showing the large field. There's a star cluster that we don't see on this image, which is providing the ionizing starlight. Let's zoom in to the surface of the molecular cloud. The starlight is coming in from the left and striking this layer referred to as the illuminated face of the cloud. The starlight goes into the cloud and is filtered as it penetrates into the molecular cloud. So we have a very dense cold gas on the right. The gas becomes ionized and warm, and then it flows from right to left, forming a decritical ionization front. So we will make a model of this. So the gas is going from right to left. The starlight's going left to right. So Cloudy works by following the starlight. The starlight is what's driving this. So we're going to go along with the starlight and set up conditions. So we have a starlight from this, take the starlight from the star, pass it into the gas, and then filter it as it goes through the gas, changing the shape of the starlight. So let's set up the model. There's one on the data.nublato. So here's we've seen this a few times, data.nublato. In the very bottom, there's workshop. Let's drill down to that. There's a number of workshops over the years, and the very last workshop here is 25 Lexington. Let's drill down into that. On the left, we see a number of directories. There's a docs directory. There's a bootleg copy of the first five chapters of Osterbrock is there in AGN3. There's a posting of the major cloud review papers and the documentation, which you also have in the main download. But what we're interested in is the bottom one, the homework. You drill down there and you see a file called M16.n. So this is the input deck that's going to run Cloudy. So this is where we've placed all the Cloudy commands. We're going to use that as the input going into Cloudy, then it's going to produce output, other files that we'll have. So we've got to grab this one. And we're going to look inside the document. Before we get started, let's think about what we have to do to do this model. This is from the Quick Start Guide. It's a quick summary of what has to be specified. We need to specify the starlight that's energizing the thing. We need to specify the gas density, the composition of the gas, whether grains are present, and perhaps the thickness of the glass. So we have to have all these things in mind. This is discussed in a few places. So let's drill into the file itself and open it. So this editor has rendered comments in red. So the sharp sign indicates that this is a comment. You can add comments anywhere you like. The black font are real Cloudy commands. So the Cloudy parser is going to work with those lines. The first line is just a title for the model. It gets reproduced in a few places. So it's just a character string. An important thing in this is going to be the starlight striking the clouds. So these are the stellar parameters. And we're working with this McLeod paper that's posted here, that's listed here. And the paper says that the brightest star in the star cluster is an O3 to O5 main sequence star. So what we're going to do is go to a standard table. There happens to be one in chapter 2 of Osterbrock and Ferland. We'll use that. And we'll look up the stellar parameters for O3 to O5. So what this is expressed here is we're just going to use a simple black body for the star. We can do far better than that, but let's do it simple here. And that's an effective temperature for this black body. That sets a shape. The luminosity of the black body, the luminosity of the star is set with the Q of H command in this particular instance. So Q of H is a number that's tabulated in standard tables. So both of these numbers, the black body temperature and Q of H, come from a table in Osterbrock and Ferland, table 2.3. So what you do here is you look up the star you're dealing with is somewhere around this, and you can get an effective temperature. And then this log Q of H is the log of the number of ionizing photons. So it's a very convenient number because this can be directly measured with free emission observations with single dish radio telescopes. So it's something you can measure. So it's something that is widely used. We just plucked out some numbers from this table. Now we're going to go here is look at snippets from the input deck on the left, and then I'm just little tiny screenshots of the part of hazy, of cloudy and hazy, the part of hazy that goes over this. So we have a radius command. By radius, what this means is the distance from the star to the illuminated face of the molecular cloud. Now, there's a toss-off sentence in the paper that says about 2 parsecs. 2 parsecs is log r of 18.78 centimeters. So we're going to set that as a radius. By this radius, this is the distance from the star to the illuminated face of the cloud. Next, we need to specify the hydrogen density. And so there's a number of density laws that are built into cloudy. HN of 3 means that the illuminated phase, the hydrogen density is 1,000 particles per cubic centimeter. But it's clear if you look at the image, it's not a constant density environment. It looks like a flow. And so what we're going to do is a hydrostatic equilibrium layer. It turns out the decritical ionization front, which is almost certainly what it is pretty close to being a hydrostatic layer. So we've done papers, and at the end of the day, the hydrostatic layer is within the uncertainties of a true decritical ionization front. So that's what we're going to assume. So the constant pressure command balances the outward pressure from starlight as it's attenuated across the cloud, gas pressure in the cloud, and trapped line radiation pressure, especially Lyman alpha, can be very important. So there's different density laws or equations of state if you want to use it fancy. So this specifies the equation of state. We're going to assume interstellar medium abundances. Uh, so this abundances command, if you say just ISM, it's going to look up a standard set of interstellar abundances and interstellar grains. You can easily use whatever you want, but this is a quick way to get something that somebody thought was reasonable. So by default, we will assume solar abundance is no grains. ISM would get you ISM depletions and classical ISM grains. It does not turn on pause. Those would be turned on separately. We have a cosmic ray background command. So the cosmic rays will be absolutely critical when we get into the molecular cloud because the standard interstellar chemistry is supported by ionizations, ion molecule chemistry. It has to be a source of ionization. The cosmic ray background is observed in the galaxy from lines of sight with H3 plus. It will have very, very little effect on the ionized layer, but it's going to be very important when we extend this model into the molecular clouds. There's a number of commands here. We're including the CMB, and that's not going to be very important here at our redshift. There's no computational reason not to include the CMB. It can have a small effect at ratio 0 on the excitation of some molecular transitions. At redshift 10, it's becoming far more interesting because it's hotter and it is a true black body. May as well include it, no reason not to. We have to converge the optical depth the rate of transfer. So iterate means to do the same model twice. You can do one sweep through the model that establishes a first guess at the optical depths. Then the second guess, the second sweep through the model, you can use those total optical depths to do a better job of the rate of transfer. So iterate is going to do two. That's would not consider to be publication quality, but it's good enough for what we're doing in this workshop. Print last iteration means only report the last iteration. There's a lot of output that's going to be controlled by these save commands, and the save commands are the primary way Cloudy gets information out into the world from this calculation. We'll talk about the save commands when we talk about running the model, but they're summarized in this section, controlling output. So with that, we'll stop here, and next time we'll run the model and have a look at some of the results.